Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, it's my pleasure to introduce John Langford, newly of Microsoft Research in our delightful New York City branch. John has been around machine learning for years, doing things like isomap and CAPTCHAs, and also doing fun sort of learning theory things like the workshop on error bounds less than a half. I remember that. That was very fun. He got his PhD about 10 years ago at CMU and was a techer back before that. So here he is.
Okay, so this is not my normal style of talk because I usually do theory, but last summer we got upset that our learning algorithms weren't fast enough. We decided to crank on it really hard. So I'm going to tell you how we got linear learning working at very large scales very quickly. So this is a true story. When I was at Caltech, just finishing up, I applied for a fellowship. I think it was the Heinz Fellowship, and they sent somebody out to interview me. And the interviewer said, "What do you want to do?" And I said, well, I'd like to solve AI. And then the interviewer said, well, how do you want to do that? And I said, well, I'll use parallel learning algorithms. And he said, no. It was more bracing than no.
Did he have gray hair at the time?
Yeah, I think so. Okay, so I obviously did not get the fellowship. Even worse, he was right to some point, to some extent. It is the case that in a race between creating a better learning algorithm and just trying to make a parallel learning algorithm, often the better learning algorithm wins, and it was always winning at that point in time. So I'm going to show you a baseline learning algorithm. This is where we started at. This is a document classification data set, which is 424 megabytes compressed. And if we look at the data set in detail, we see something very typical. We have a class label, then we have a bunch of features, which are TF-IDF transformed feature values. And then on the next line, we see another example, and so forth. Right? So this is very typical. And now I have a 6-year-old laptop with an encrypted hard drive. How long does it take to actually learn a good classifier on this data set?
One class. One class.
We have two classes.
Two classes. Two classes. Not multi-class. Two classes. Linear classifier? Oh, I don't know. 15 seconds.
15 seconds would be nice. On my desktop at home, which is not 6 years old, it takes about 2 seconds. On this machine, maybe 40 seconds or so. So what's happening here is this is progressive validation loss. So we're running through the examples. We evaluate on the example. We add that into the running average. And then we do an update, right? And I guess the important thing about this is that the deviations are like a test set when you're just doing one pass over the data. It turns out that for this data set, if you have a TF-IDF transform and you have a very tricked out update, linear update or online update rule, which we have, you can get an average squared loss of 4% or 0.04. And then it turns out on a test set, it's about 5 1/8% error rate, which is about the best possible anybody's done on this data set as far as I know. Okay, so this is the baseline. This is where we're starting from. It was only 31 seconds. So very good. Okay, so we're just learning a linear predictor. And document classification is particularly easy because words are very strong indicators of document class. There are roughly 60 million features that we went through, 780,000 examples, and it took about 31 seconds this time. Okay, so that's nice. But we have bigger data sets. So in particular, at Yahoo, we were playing around with an ad data set, which had 2 Terra features. So I should go back a little bit. Let's go back here. This is one feature. Everything that's not there doesn't count as a feature. So we're only counting the non-zero entries in the data matrix. This is a sparse representation. So when I say 2 Terra features, I mean 2 Terra sparse features. So 2 Terra non-zero features. Right? We still want to learn a linear predictor. It will have a lot more parameters because you need to have that. And here's a few more details. There's 17 billion examples. There's a little over 100 non-zero features per example. There's 16 million parameters that we're learning. And we have a 1,000 node cluster to learn on. And the question is, how long does it take? Well, how do we do it, first of all? But more importantly, just how long does it take to do it?
You mean a terabyte of features?
Nope.
Or?
I mean a Terra feature. 10 to the 12 non-zero entries in your data matrix.
You say 16 billion parameters. What are the parameters?
So those are the weights.
The WIs.
What's that? Yeah, WIs.
So there are that many features that are non-zero ever, or you mean that in summed over all the cases?
There's this many non-zero entries in your data matrix. So the number of bytes, if you use a byte representation, would be maybe 20 terabytes, perhaps, if it was 10 bytes per feature.
Is that just 17 billion times 16 billion? That's how you count it.
No, it's the number of non-zeros.
That would be dense.
So your total matrix is 17 billion times.
Oh, yeah.
So it's 17 billion rows and 16 million
Yes.
columns, and the number of non-zero entries is 2 tera.
Do you have to worry about overfitting? Can you have 1,000 times more examples than unique weights?
Yeah, so overfitting becomes less of a concern, but it actually is some concern. The issue is the sparsity. So some of the features just don't come up very often. And so it is possible to overfit in those features, even if you can't overfit on the majority of the mass.
And you're doing something about that, and you'll tell us about it.
Yeah, but let's just go back to the demonstration, right? So I'm using zero regularization when I do this. And it turns out that if you have a very good online update rule, you don't need to worry about regularization that much. It's kind of built into the online process itself.
It's one of those neural net things you wouldn't like.
Any kind of regularization is fine, or fuzzy regularization.
So the question is, how long does it take?
30 to 40 seconds?
That would be fantastic.
Sadly, no.
Turns out those extra zeros really matter.
You told me the answers.
Yeah. 20 minutes would be nice. I can't quite do that. I did 70 minutes. Okay, so now the important thing here is that if you just look at the overall throughput of the system, we have to do multiple passes on this data, by the way, because it's much rawer than the document classification data set. So if you look at the overall throughput, this ends up being 500 mega features per second. Each individual machine in that cluster just had a gigabit per second Ethernet. Now, I don't know exactly how many bytes it takes to specify a feature, or bits, but it's certainly more than 2. So we are beating the I/O bandwidth of any single machine in our network.
Do you keep the data in binary, or do you keep it in ASCII? Maybe just.
We're starting from ASCII.
So you're actually passing over the ASCII multiple times?
No. Yeah, there's a lot of tricks that we throw in, right? But we do start from ASCII. because that's kind of human readable and it's debuggable. But the VW has a nice little cache format, and I actually kind of lied here because I was really using the cached form of the data set, which is, of course, unreadable. Oops. So it's 290 megabytes in binary. Okay, so this is the only example I know of a learning algorithm which is sort of provably faster than any single machine learning algorithm that's ever invented in the future, because we beat the I/O bandwidth, right? We beat the I/O bandwidth limit. That's finally an answer to this guy that turned me down. All right, so we had a book with Misha where we were, or people contributed many chapters on parallel learning methods. And for each of these parallel learning methods, you could take a look at sort of the baseline they compared with in this features per second type measure, and then how fast their system was. So this was some people at Google. They had a radial basis function support vector machine. They were running on 500 nodes using the RCV1 dataset, the same one that I just showed you. And they had some speed up from a relatively small baseline. This was an ensemble tree. This is NEC guys. They had a much stronger baseline support vector machine, and they sped it up more than you might expect. They only had 48 nodes. This is more than a factor of 48. This is a logarithmic scale here. And they're winning from some nice caching effects. This is MapReduce decision trees from Google. They have some reasonable decision tree baseline, and then they just speed it up in a pretty straightforward way. This is from Microsoft. This is Krista and Chris's boosted decision trees. So they were working with a relatively small number of nodes, only 32. They had a very strong baseline, and then they sped it up a little bit more. And then this is what I just demonstrated to you. And this is what I'm talking about now. So the baseline got worse because the data set is raw, and we have to pass over the data multiple times. Right? So we can no longer do a single pass. We get a much bigger speed up because we're dealing with 1,000 machines, effectively. Okay, so how do we do this? Well, we do things in binary. We take advantage of the hashing trick. Who knows the hashing trick here? Okay, so the idea with the hashing trick is that if you're dealing with, particularly if you're dealing with these mini features type data sets, you can often just hash the individual features to map them into some particular fixed dimensionality weight vector space, right? So when I say 16 million, I don't mean that there are 16 million unique features. What I mean is that I'm using the hashing trick to map them to using a 24-bit hash, right? And so what's scary here is that you get collisions between different features, but turns out that if your features are a little bit redundant, that works out pretty well. And the machine learning algorithm can learn to compress around collisions. We're using online learning, using some implicit features. We're doing a bunch of tricks to improve the online learning. We're using LBFGS to finish up with batch learning. And we switch between these two. And then there's a bunch of tricks in how we're doing the parallel learning as well, all of which are aimed at either making the communication faster or making the learning a little bit more intelligent in a parallel setting. Okay, so the key thing that we did, the most key thing, is this Hadoop all reduce, which I'll go through first. Okay, so all reduce is an operation from MPI. Who knows all reduce? Okay, just a couple. So the idea is you start with a bunch of nodes. Each node has a number. And then you call all reduce, and then every node has the sum of all numbers. Right? And now the question is, what is the algorithm for doing that? And one such algorithm is you create a binary tree over the nodes, and then you add things up going up the tree. So 1 plus 2 plus 5 is 8, and 3 plus 4 plus 6 is 13, and then 8 plus 13 plus 7 is 28. And then you broadcast back down the tree. Okay, so that's all reduce. And this is a very nice primitive in several ways. In a network, in general, you have two things that you care about. One of them is latency, and the other one is bandwidth. Typically, in machine learning, when you're calling all reduce, you don't want to call it on just one number. You want to call it on a vector of numbers. And so you can pipeline the all reduce operation, and then latency doesn't matter. Right? The other thing, then there's also bandwidth, and this particular implementation of all reduce is within a constant factor of the minimum. So for the internal node, you have 1, 2 coming in, 1 going out, 1 coming back, and 2 going out. So that's 6 total, 6 times the number of bytes that you're doing all reduce on. So that's within a constant factor of the best possible. And so we're decent as far as using our bandwidth. Okay, and then the last point is actually the most important one. The code for doing this is exactly the same as the code that I just used here. It's exact. I mean, I wrote no new functions except for the all reduce function itself. And I can just look at my sequential code and go, okay, I'll do all reduce there, and then it runs in parallel. Okay, so this is one of the few times in my life when having the right language primitive seemed like it was phenomenal. And this comes after I spent several years doing parallel programming the hard way. So it's very easy to experiment with parallelizing any learning algorithm that you want using all reduce. Okay, so here's an example. If we're doing online learning on each individual node, what we could do is we pass through a bunch of examples, doing our little online updates, and then maybe we finish with our pass, and then we call all reduce on the weights, then we average our weights, and then maybe we do another pass. Right? And so we just add this. If we're doing things in a sequential environment, there would be no all reduce. And then when we want to do things in parallel, so we just add in the right all reduce call. Okay, so we did this for the other algorithms that we're using. This is simple stochastic gradient style algorithm. There's also, well, it gets a little bit more complex. We want to have more intelligent online update rules, which keep track of some notion of how much update has been done to an individual feature. And then you want to do a non-uniform average of the different weights, because that makes sense. The weights which have seen this feature more often and updated more for that feature should have a stronger weight in the overall average. Right? So it turns out you can do non-uniform averaging easily enough. You need to use 2 all reduce calls. And you can do conjugate gradient, and you can do LBFGS. Okay, so that's all reduce. That's what MPI gives you. We're not actually using MPI. And the reason why is basically MPI was not made with data in mind. So typically, if you tried to use MPI, you'd have this first step, which was load all the data, which would be pretty painful. And anyways, the data at Yahoo existed on Hadoop clusters. So you didn't want to shift the data off the clusters because the data was very heavy. So what Hadoop would give you is the ability to move a program to the data, right? And rather than moving the data. And that's very nice as far as resource usage. And then another thing that Hadoop would give you is automated restart on failure. So with MPI, if one of your nodes goes down, typically the job fails, right? And that's actually still true for us with all reduce, but it's not as true. And in particular, it's not true for the first pass of the data, because we delay initialization of the communication infrastructure until after every node has passed over its piece of data. And that means that the most common failure mode, a disk failure, will get triggered in the first pass. That job will get killed, and then it will be restarted on the same piece of data on a different node. And then with respect to the overall computation across the cluster, all that happens is things are slowed down a little bit in the first pass. Right? So this deals with the robustness issues to a large extent in practice. My experience was that as long as your job was less than 10,000 node hours or so, you didn't see failures, unless they were your own bug.
After this.
What's that?
Was the 10,000 node hours before this or after this?
It was after this, but I can't entirely ascribe that to this. There's another effect, which is some sort of convention in Unix land that the ports above 2 to the 15 can be randomly used, and we were using those on purpose, but so there were collisions going on. Anyways, that change also happened, and then all of our problems went away. Yeah?
So the data's already been pre-partitioned across the nodes, and then you have multiple copies of each sort of chunk of data.
That's right. So Hadoop has a file system called HDFS, which just stores everything partitioned across the nodes in triplicate. Yeah?
So 2.1 Terra features is not a lot if you map it to 1,000 machines each, right? It's like 2 gigabytes per machine.
No, more like 20 gigabytes perhaps, but yeah.
20.
The feature is not a byte. Feature is more than a byte typically.
Okay. So
You're right. It's not terribly much on each individual machine. That's good.
So I'm just questioning, is MPI really horrible? Because it seems like if you are delaying initialization on Hadoop, anyway, you can do the same on an MPI cluster.
So MPI is basically not an option because we didn't have the cluster. We didn't have a separate cluster to run MPI on. And an MPI kind of, it doesn't have a resource scheduling component like Hadoop does. So a big company that wants to make sure that its cluster is getting utilized isn't going to want to run MPI because they want to share machines as much as possible. There were various efforts at Yahoo to run MPI on Hadoop. It was never pretty. Okay, so there's one last trick which is very important. When you have 1,000 nodes, all reduce is a barrier operation. That means you run as fast as the slowest node, right? So if you have 1,000 nodes, one of them is going to be kind of slow. In particular, it's common for the slowest node to be a factor of 10 slower than the fastest node, maybe even a factor of 30. So Hadoop has a mechanism called speculative execution, which says that if one of your jobs is running slow, you restart the same job on the same date on a different node. And then these two processes race. So we take advantage of that. And that allows it, it's a factor of 10 improvement in the overall speed of the system. Right? Yeah?
So the mapping is kind of, you actually have exact copies on different nodes and still the speed is different.
Yes, you have exact copies on different nodes. And the second one is starting later than the first one because the first one has been noticed to be slow. So we're going to lose a factor of 2 or 3, which is actually what we observe compared to a single machine performance. But we don't lose a factor of 30. And that's a big win.
So I guess the question was, so the speed, the factor of 30 slowdown, isn't that particular data was bad in some way, it's something else?
No, typically what happens is, the data is on individual nodes. The resource scheduler tries to figure out which nodes to move the computation to. Occasionally it moves both the data and the computation, but mostly it just moves the computation. And often it tries to oversubscribe individual nodes for performance reasons, overall throughput of the system, and it fails, right? It fails badly on some particular node. Or maybe some node happens to have more than one piece of the data, right? And in which case it gets overloaded, right? So these kinds of things come up very commonly in a large cluster. Yeah?
Did you have the cluster in exclusive use mode, or were you the only job running on the cluster?
No, they gave us access to the production clusters, well, not the actual production clusters, but the development clusters, the ones that were used, right? And They gave us access, and they let us use 1,000 nodes, but maybe even 2,000. But exclusive access was too much to ask for. All right, so this is reliable execution at about 10,000 node hours. We only went to about 1,000 node hours, and so maybe there are larger scale problems here. One thing that we checked, by the way, there's a lot of cheap tricks when you're doing large scale learning. You could, for example, subsample the data, and run on the subsample data. Turned out that for this data set, you actually did do worse. We subsampled, and noticeably worse. Like.
Initialization to...
In fact, this was already a subsample data set. This is throwing out 99% of the non-clicks. But we couldn't throw out any more without losing performance.
Would you be any faster to use the subsample data as an
It's possible. It's possible. The thing which is a little bit tricky is that the communication time is non-trivial here. So if you subsampled the data set and then you ran on 1,000 nodes with a subsampled data set, the communication time would still be eating into your total time budget quite a bit.
You have to spray 16 million parameters at 1,000
Yeah.
nodes.
So that's like a second or something on a gigabit per second network. It was in fact maybe about 10 seconds in practice, because there's collisions and whatnot. And also we have that factor of 6. Okay, so what am I doing? No, wrong way. Okay, so that's the communication infrastructure. Having a decent communication infrastructure is necessary, but not sufficient for a good machine learning algorithm. This is radically better than MapReduce, because, at least for Hadoop, the iteration time for MapReduce is about a minute, and here is about 10 times ping. So you can, just in terms of performance, it's much, much better for synchronizing different nodes. It's also much, much easier to program with allReduce, which I think is probably an even more an important thing in practice. Yeah?
So you said you did work using an MPI infrastructure that you coded your own allReduce program?
Yes. And we coded it as a library. So it is a library in VW, which is an open source project that we ran. So it's very easy for you to just use that library. It's one file that you just grab and stick into your, it compiles as a library, in fact. So it should be very easy to use if you wanted to.
What does it do when it has MPI issues, like somebody's not there cooperating with everybody else broadcasting?
The failure modes of allReduce are just the same, except that the interface is set up to encourage delayed initialization, because when you call it with all the things it requires to initialize, right? It works with speculative execution, so it does. If two nodes say, "Hey, I'm node 3 in computation 4," then it just takes the first one and uses that, and it ignores the other one. In order to make this all work, you need a way for the nodes to organize themselves into the tree. So the way that works is there's a little daemon that runs on the gateway. And then for every map job, we point it to the gateway. So the job talks to the daemon and says, "Hey, I'm job 3, and I'm 3 of 4, with some particular nonce, which you need to have distinct for each different allReduce invocation." And then once it collects a complete set of 1 of 4, 2 of 4, 3 of 4, 4 of 4, then it tries to be intelligent about creating the tree. So it sorts the IP addresses, and then it builds the tree on the sorted list of IP addresses. So that means in particular that if you have the same job at the same IP address, then there tends to be communication just inside of a computer, right? It's not guaranteed, it's not perfect, but it tries to minimize the inter-rack bandwidth usage.
Does it do this for every allReduce iteration?
No, it does it once, the initialization, and then it just keeps the sockets open for overall usage. So once the communication infrastructure is created, if a node dies, then the overall process dies. But again, that wasn't a problem out to about 10,000 node hours. Okay, so now let's talk about the algorithms. We're trying to do gradient descent. Gradient descent is the core of all of these algorithms. But gradient descent is not quite adequate. And the way I think about it not being is inadequacy is to think about units. So it's kind of a physics point of view. So if you have squared loss, you can take the derivative of squared loss. Then it looks like this. And the important thing is this is like a constant here, and then we have the feature. And if you look at the prediction, this is the feature times the weight. So that means that if the features double, the weights need to halve in order to keep the same prediction, right? And this is a feature. So we're adding a learning rate times a feature to something which is inverse in the features unit-wise. And that unit clash causes issues.
Well, that's why people use normalized LMS where they normalize out. They try to make the x unit vector. They try to divide by the norm of x.
Yes, in fact, that's one of the tricks.
Okay, that's an old algorithm.
Yeah, it's a simple thing. Right, so W has natural units of 1 over I, and Xi has units of I, so things don't work very well. So you get updates that are just too far in a particular direction. Okay, so we're doing adaptive, safe, online gradient descent. So online, you're aware of. You just update after seeing each individual example. Adaptive is where the update in direction I is rescaled according to 1 over the square root of the sum of the gradients squared for that feature. So you have essentially a per feature learning rate where the learning rate gets scaled down as you do more and more updates to that individual feature. Yeah?
Does this relate to all these algorithms for second order algorithm for linear learning?
Yeah, so in terms of performance, my impression is this is at least as good. In terms of the actual update rule, it does differ in some details. So we're looking at the gradients here. So it could be, there's two reasons why the sum of the gradients is small. One reason is because you've never seen that feature before, which is helpful. And I think the second order gradient descent approaches get at that pretty well. But a second reason why some of the gradients might be small is because every time that feature came up, you predicted it correctly. In that case, the update rules tend to differ in what they do.
You have the CW, the
confidence weighted?
Yeah, confidence weighted, which kind of works along the same lines.
The real truth is I haven't tested empirically to compare the two. I would like to do that, but I haven't had time. Anyway, this is what we're using. That's helpful. Another thing is the trick that you mentioned. So rescaling the features to where the units work out overall. That's helpful. And then the last one is these safe updates. So this is when Nikos visited me, we're worrying about doing online learning with large importance weights. And the obvious way to deal with an importance weight, you want to, if you have an importance weight of 2 on an example, it's like saying this example is twice as important as normal. And the obvious thing to do would be to just put a 2 here, right? But that works pretty badly. Essentially because you're trying to have a very aggressive learning rate with online learning. And that makes it too aggressive. So instead what you can do is you can say, all right, a example with importance weight 2 should be like having 2 examples with importance weight 1 in a row. And then you can say, well, maybe this should also be like having 4 examples with importance weight 1/2 in a row. Or maybe it's like 8 with importance weight 1/4 in a row, and so forth. And then you can take the limit of infinitely small updates, and you can solve in closed form to figure out what that update rule would be. So the important thing about this update rule, for our purposes, is, okay, so this does in fact help you with importance weights. But we don't have any importance weights here. Turns out that it also helps with just importance weight always 1. Because it's not equivalent to just the normal update rule. It takes into account the global structure of the loss function.
That's why you have to use square loss.
It doesn't have to be squared loss. We've solved it for many other losses, logistic as well. In fact, the starting example was actually logistic loss. So it's safe because if you have these infinitely many infinitely small updates, the update can never pass the label for any of the same loss functions. And so for hinge loss, for squared loss, for logistic loss, the update never passes the label. So you never have a large importance weight throw you out into crazy land. And that allows you to have a much more aggressive learning rate than you could otherwise have, even with just importance weight 1.
How do you enforce that at the higher? I mean, so you're doing that locally, like for each guy as they're stepping through on a given node. How do you enforce that at the? Can you enforce that at the higher level as well when you combine them?
So we're just using distance inequality to make sure that combining makes sense, right? So, yeah. Okay, so we do online learning on each individual node. We use all reduced to average the weights. Then we switch to LBFGS. So LBFGS is an algorithm that I did not learn about as a grad student, and I feel like my education was missing something.
It was just being formulated when you were a grad student, I think.
No, I think actually LBFGS was 1980.
Oh, LBFGS or
yes.
BFGS?
BFGS was 70. LBFGS was 80. It's easy to remember that way. So LBFGS is a batch algorithm. Batch algorithms suffer a lot in terms of speed, but it turns out that it's very good at getting that last bit of optimization done well. It uses, so what you would want to do, if you could afford it, would be something like a Newton update. But that involves inverting a Hessian. You can't even represent a Hessian on this many parameters. So instead what you do is you approximate the inverse Hessian directly. And this is the core approximation. So you have the change in the weights from one pass to the next, outer product with a change in the weights. Then you have the change in the weights, inner product with a change in the gradient. And this, if you think about the units for a moment, actually has the right units. It turns out to be a pretty decent approximation to the inverse Hessian. So then you build this up over multiple rounds, and you get a better and better approximation to the inverse Hessian. And then you can converge very quickly to a good solution. Okay, so now we use the average of this output to initialize this, which is a cheap trick that turns out to be extremely helpful. Okay, so now we use a map-only Hadoop job for process control. We use all reduced code to synchronize the state. We save input examples into a cache file for later passes. And we use a hashing trick to reduce the input complexity. These are all very important things individually, but they're not related to the actual parallelism. And then it's open source in Vopal Wabbit. This is the online learning software that we've been putting together. Now, I guess it's online and batch learning now. Okay. We did a few studies of this system. So we had a smaller data set, and we varied between 10 and 100 nodes. And then for each number of nodes, we ran 10 times. And then you can look at, so if things were perfectly linear in their speed up, then it would look like this line. We're not perfectly linear in our speed up. Things do go a little bit slower as you go towards more and more nodes. But you do get significant speed ups. So this is between 10 and 100. This takes a factor of 10 longer to compute, or almost a factor of 10 longer to compute than this does. You can also look at the variation between the min and the max running time. And you can see there's some variation. You have to expect that on a cluster that you don't really control, but it's not too bad. Okay, so now we can look at how this algorithm works. There's two really obvious things to compare with. One of them is, what if we take our online learning algorithm and we just do repeated averaging? There was a paper people published about this kind of approach. And you can see that things do indeed get better over time as you do repeated averaging of online learning. And it's still getting better out here at 50 passes. And then another approach you can do is you can just say, okay, I'm just going to run LBFGS. And it does nothing for 10 passes. And then it starts to get better and better and better and better. And it keeps getting better. And then you can do online learning for 1 pass. And you can switch to LBFGS. And then you're done at about 20 passes. This is a splice site recognition data set. This is one of the largest publicly available linear prediction is reasonable type data sets that I know of. It's probably the largest that I know of. You can also do online for 5 passes and then switch over to LBFGS, and you see that maybe it tops out a little bit later. So in our experiments, it seemed like 1 online pass was pretty good at putting you near enough to the optima that that LBFGS would really nail things pretty quickly. We compared with various data sets, or with other algorithms. So there's a couple other algorithms. One of them, I think maybe Marty gave a talk about here before. The other one, Lynn and Ofer worked on, and Ron. And who was the 4th author? What's that? Oh, yeah, that's right. Okay. So Marty's algorithm operates by essentially an overcomplete partition. So a single example appears on 1/4 of the nodes. And then you learn independently on each of these nodes, and then you average things together at the end, right? And this is essentially measuring, this is effective number of passes. This is measuring the degree of over completion of the partition, right? So at 5, an example appears on 5 nodes. And then there's the mini batch approach, and in here we're just measuring the number of passes through the data because we keep passing through the data multiple times, doing the mini batches. And LBFGS really helps you kick that last bit of performance, and that's a pretty big win.
And the time on LBFGS is still dominated by the gradient computation.
Oh yeah, by far. So the actual LBFGS itself is like a second or less.
And do you run that just on 1 node, or do you run that?
It runs on all nodes.
I see, because
it's all reduced. Yeah. So we look at sort of the communication computation breakdown for the system, and it's about 10 seconds to do the synchronization. It's about a second or less to do the LBFGS itself. The slow node problem is still there. So there's about half of the time is wasted in a barrier, and about half is for computing the gradient.
What is the memory size for LBFGS? How many?
You have to look in the paper. I think the default in VW is 15, but we often used 5 or 10. Yeah. This is, by the way, this graph kind of understates the difference in performance between these algorithms, because if you look at computational time, this would be substantially worse. This one would be much worse because the communication complexity is higher. This one would be significantly worse. Okay, so I'm about done. We decided to make a new machine learning mailing list, machine-learning, because we had that at Yahoo, and I found it useful for interacting with product groups of various sorts. So I think many people will be automatically subscribed, and you can unsubscribe yourself. But if you are talking to product group people that are doing machine learning, it'd be cool to point this out to them. VW, you can just search for. There's a mailing list that's external. If there's demand enough, we can create an internal one. I'm trying to work with Misha to create a Windows version, hopefully this week. And there's a tutorial at NIPS, which is off the wiki. Since this is my first talk here, I wanted to mention a few other things. So there was CAPTCHAs and ISOMAP that you mentioned. I've also worked on learning reductions, which is how to decompose complex prediction problems into simple prediction problems, such that the solution to simple problems gives you the solution to the complex problems. We're implementing these in VW right now. Some of these are also logarithmic time reductions. So if you're trying to do multi-class classification, most of the common approaches take order k time where you have k classes. Turns out that you can actually do log k effectively in many situations. We've looked at active learning. So this is the selective sampling version of active learning. And I guess the thing that we figured out here is how to deal with noise. So we can deal with the same kind of noise that you typically analyze in supervised learning settings with active learning, right? And we have algorithms now that are very efficient and effective. And then there's a lot of work on contextual bandit settings where I guess the motivating example at Yahoo was ads. But anytime a user comes to a website and the website decides something to show the user, and then the user reacts to that, you can try to use a machine learning to predict what the website should be presenting to the user. And there's a bunch of issues related to bias and exploitation around that we've solved to a large extent. All right, thank you.